So, we start today's lecture pretty much with two continuous and while doing this you have to look at this at the what is the f for r squared, a suitable sigma field for r squared. What is this, right? That is what we first have to look at. Why are we interested in r squared? Basically we are interested in r squared because r squared is a minimal space that we require to define two continuous random variables. If you have only r, right, you cannot and you let us say you define x of omega equal to omega, that is you have defined a standard random variable on a single, right, for omega is a single real measurement. Then once you observe the measurement there is no more randomness, right. You cannot define yet another random variable and expect it to be truly random separately of x. So with just r you are completely limited in that you cannot really go beyond one random variable. So if you want to go to if you want model situations where there are two measurements, right, each of which can vary to some extent independently or separately from each other, and where looking at one measurement you don't know you don't know the other one fully and completely. You know something about the other one but not everything. For that you need to consider at least r squared, if not bigger spaces like r cubed or r whatever, right. So we have to make the jump to r squared from r, which is basically the plane xy plane, and we need to look at the events the sigma field, or right, what events we are going to define in r square for which we are going to assign probabilities, right, and those events are basically regions. The events in r squared are like we had intervals in r squared we have regions. And what kind of regions are these? These regions are basically anything that you can get by taking a countable union of rectangles. What is a region? And again, to make life simple for us, we will start out with the most basic rectangle that we can think of, right, which is basically dx dy, right. You start with, again I repeat that kind of figure, if I start with dx dy, this is an elementary rectangle, and not only is it a rectangle, it is also aligned. What do I mean by aligned? Its sides are parallel to the x and y axes, right. So this is a simple aligned rectangle. And what kind of sets can you build with such rectangles? It turns out you can build pretty much any arbitrary region, right. So if I have something like this, some region like this, how do I express this, right, that set of points in the xy plane as a countable union of such rectangles? Turns out I can divide the thing like this, right, and in these portions I can look at finer and finer divisions of the xy plane and ultimately obtain any funny shape, right, almost any funny shape as a union. The point is that we need this countable union. Of course there may be an uncountable infinity of points in the plane, just like there are uncountable infinity of points aligned, so we cannot think of taking the union of individual points, right, that is not a countable union. But if you want a countable union, we allow these rectangles to be arbitrarily small, right, and so again I am not expert in this kind of thing at all. I am just 2 or 3 places that I have read this business, they say that with such rectangles you can generate just about any region we care about. So I am just going to repeat that argument here. Standard counterintuitive statement is a circle is a union of rectangles. Now again you can take that for whatever it is worth, but well actually you have to take it as that it is true, right. So we are going to assume that statement is correct, right. A circle is the union of rectangles. Now do not ask me if a rectangle is the union of circles, but anyway. So this includes circles. Basically I think this goes back to when you studied multivariable calculus, right. You can, if you do the integral, what is this integral dx dy? Basically by doing a countable union we are doing this. This is a countable union, just like integral dx is a countable union of intervals. But integral dx does not seem to have the it's too trivial, right. You can just say, well, it is going to integrate to the length of the interval or whatever. But here this is something more interesting than just a linear putting together of intervals, isn't it? This is dx dy. So what does this double integral give you? If you perform this over a certain region D, it gives you the area of the region. Go back to your multivariable calculus class and check it out. So you take a region which is a subset of the plane. The fundamental identity for finding the area of such a region is to do this double integral, where of course the boundary would be defined by for some function y as a function of x and so on, and that would come into the limits of this integral. So also consider intersections. So what do you get when you do intersections of rectangles and then unions of these intersections? So what can you generate from this? You can generate curves. Right, generate not just curves, you can also generate individual points. Sets, right, I would say, what did I write here? Countable union of points. You can also generate a countable union of points. You can generate curves, comma, points, and then from this you can generate countable union of points. How do I get a point? My point is the intersection of 4 rectangles, if you wish, right, where the boundary is included in each rectangle. Just like a single point in the on a real line you can think of as the intersection of 2 intervals exactly intersecting at that point. Similarly, a point on the plane you can think of as the intersection of 4 rectangles, whatever. Okay, and so the case that we looked at earlier, the 2 discrete random variables, is obviously included here, except that we do not need to do all this for that, where we are only looking at only points, right. In discrete random variables we only look at points, you are not interested in intervals, you are not interested in more complicated regions and so on. So for that you do not need to, if you are going to stop with that, you do not need all this at all, because you will say every countable every set is a subset, is a valid event, and so you do not have to worry about anything basically. But so this is a much bigger thing, obviously, right. It includes the union of points, it includes curves, right, and it includes any complicated combination of regions and points and so on. So obviously you can generate an enormous variety, or whatever, almost everything of engineering interest can be generated this way. Right. We are most interested, at least for right now, in regions, because that is where continuous, so our main interest is regions, right. not curves. This is regions, and there are two regions with, let me say, area greater than 0, not equal to 0. How do you distinguish a curve and a region? A curve has what? Area equal to 0. I cannot, if I do this type of a double integral, if I write it in the limiting sense for a curve, it will collapse to 0. So we are right now interested only with regions with having the area could be infinity, but it's not 0. And we also note that even the set of points, let us say, how do I write this, minus infinity x naught, supposing I just look at minus infinity x naught, right, this interval, this corresponds to what? This entire, I am not talking any random variable right now, assuming I have the axes x y and I pick some number x naught. This interval minus infinity, interval just by looking only at this, only at the variable x and not looking at variable y, generates a half plane, the portion of the plane that looks like this. That is also a valid region. So this is, so minus infinity x naught, minus infinity y naught, a comma b on a less than x less than b, all these, right, all such things are all valid. You can also add c less than y less than d. See all of these, right. So if we think of it as an event, we should put the curly brace around it, but for right now I am just looking at a valid region, so I am just writing it with ordinary brackets or parentheses, right. Later on we are going to look at the event version of this. So what happens is that because these are all regions. Now if you look at the random variable extension, we can clearly say that, right, there won't be any difficulty in assigning, if we can assign probabilities to any region in the plane, then these also will have probabilities assigned to them, and therefore all the theory we have studied so far will not get upset by this kind of a definition. So the question is, how do we assign probabilities to arbitrary regions? So once you answer that question, then we are home, right. Okay, so this is, so up to now I have not talked about any random experiment or anything of the sort. I am just looking at the plane and how to look at regions of the plane, that is all. Now we bring in, right, the plane as the sample space of an experiment, right. Some omega is a subset of the plane. This is, let us say this has finite area. This itself is a region, right. This omega is itself some, it need not be the whole, right. The set of points that we get in the experiment need not be the whole plane, just like in the real line case we could get some portion of the real line. So like that, right, we start with some sample space omega, which is itself a countable union of rectangles, so allowed region, in other words, right. Obviously you do not want to start with something which is some funny thing, right. So this omega itself is a well behaved region in this sense that we have talked about all along, right. And so here is a region with area greater than 0, right. So each omega in this is what is basically has two components, omega x and omega y, if you will, right. It has an x component, or it's basically you can just write it as x comma y, and right. So every omega is basically has an x coordinate and y coordinate. You assume that the axes are marked. Here of course you can say, well, at this point there is no axis, but for for making the measurement you need the axis, you need the origin, you need the x axis and y axis. Without that you can't define the x value of the measurement and the y value of the measurement. So if you for example throw a dart at a plane, which is most standard or the start one of the simplest so the dart comes and lands here. What is right? So unless you have the axis defined beforehand, you cannot talk of the x coordinate of the hitting point and the x and so on, right? Okay. So this is so every omega is associated with some x x and y and now we define the two random variables capital X and capital Y, right? So we said this implies, right, if this is true, then omega equal to omega y, you can just forget about the you can just directly write as x y, you don't even have to look at this, right? So now which means that I can define x of omega as small x and y of omega as small y. So for every omega I've defined the values taken by the two random variables. So if I do this for all omega, small omega and capital omega, I have defined the two random variables x and y. And obviously this can always be done. So are these now so therefore now x and are they jointly are they two random variables now or not? Clearly, as we said earlier, okay, now we bring in the region. So we are going to assume that every region is going to have a probability. How we are going to calculate that probability will come to a little later. But since every region has a probability, this intervals on the x axis and intervals on the y axis also have probability. So therefore there is no problem here in claiming that x and y are two random variables, right? You can always say that if every region has a probability, then every interval on the x axis and every interval on the y axis also will have a probability, right? So therefore these are two random variables, right, when every region, this is not just omega, also the whole plane, right, by extension. We are going to do the domain extension thing that we did earlier, right. So this is the most important idea here, right. You can always take components of the space as random variable when you are going to assign every region a probability, right. So there won't be any theoretical issue that you are going to run up against. So the question is, how do you assign probabilities to regions? You start out with you assume that the region, as I said, for now we are going to assume that region has area 0, that omega itself is right, the capital omega has area greater than 0, and for every non-zero region we are going to do a double integration, right.